Okay. So where we were? We were here. Okay, good. So let's try to quickly go through this. So Bayesian ANOVA. Well, ANOVA is not the proper name, although it's commonly we commonly speak about Bayesian ANOVA, although it's not an analysis of variance. This is the reference paper for the basic methods of this Bayesian ANOVA, and the idea is just calling ANOVA because typically in the frequencies world, when you have a factorial design or you have different predictors for something, there's this used to call ANOVA, even if it's not. When there it's real ANOVA, but in this case no, but it's easier to make parallelism between the two. So that's why it's called Bayesian ANOVA. In general, we can refer to this, thinking of this as in any case, an hierarchical model. We will see later more details on that. So I don't go into the details of what is a mixed model or multi-level model or all the other names of this kind of stuff. So don't go there, but just think this one as, okay, I have the t-test, fine, two conditions, one against each other. When things get more complicated, I can use the ANOVA. You can do it in JASP. It's pretty easy to run this kind of analysis, although there starts to pay the lack of flexibility, the software. So you can do something if you are going with basic design, with basic assumption, with basic priors. As soon as you want to manipulate something, then you have to switch to R. And you can do also in R, both with bias factor, but I wouldn't suggest bias factor if you have this kind of design. I would suggest to use the RMS, which is a little more complicated as a package, so we are not going through this. But I prepared a small file, R file, that we will upload, maybe Julia will send you, with just one example in bias factor, one example in the RMS. So if you want to approach these packages, there are also stuff there. Here maybe we can quickly go through the JASP part, but not just with the JASP. So okay. So if you go to JASP, you find your Bayesian ANOVA under ANOVA. You have the frequentist and the Bayesian one. You have repeated measure. Repeated measure ANOVA is good even if you have mixed design. You can use the repeated measure menu. In this case, it's a mixed design. I just opened one file from the library here. So data library, ANOVA. There is bulk, if I remember, but you can try with whatever you want. And we have this 2x2 design within, plus gender has an additional factor predictor. So the first analysis is a classic ANOVA. You have your output. We don't go through this one. If you go to the Bayesian part, what it actually does is a model selection. So basically you have all the models with all the different predictors, and you try to understand which models is more likely to predict your data. So you have, for example, in this case, you can see here, maybe it's too small, but I guess I have also the slides with that. Yes, but it's not bigger. Okay, so stay here. Here you have the list of all the possible combinations. So we have frighteningness, disgustingness, sorry for the bad words, but that's it. You have frighteningness plus disgustingness plus gender, so three main factors. Then you start to have one interaction. So you have all the combinations. This one, of course, the longer is the one with all the different interaction at all the different levels. And now the interesting part is to look at this part. So what is this? P of M is the probability of the model before looking at the data. And in the case of of the Bayesian model in JASP, you attribute the same probability to each model before running the analysis. So you see that it's the same for all the different models, which is basically 1 times all the different models. By all the different models. Then you condition your model on your data, basically, and you have a probability of the model given the data. Okay, so after I observe the data, what's the probability of the frightness plus disgustingness model in the context of all the models that I have here? Yes?
Or even that it's not so well seen, can you show us how to put it
yes,
in the
yes.
Maybe it's better to...
Yes, so, okay, this is the interface for the repeated measure ANOVA. This is, I don't know if you're experienced with SPSS or other software, it is exactly the same method to add the different levels. So here we can add a new factor. For example, we may add another repeated measure factor clicking on, on RM factor 3.
Maybe you can press Windows and plus and make it.
How? Like,
I'm not sure that it's possible.
No, I don't think it's working. Maybe open something else. Oh, yes, it worked.
It brings a lot
that's a good, wonderful. Okay. I don't know how to go back from this situation, but...
There are Windows menus.
Thanks. Okay, good. So by clicking on repeated measure factor 3, we can add a factor, but we don't have anything to add here. So we had one factor, frightness, with 2 levels. Here you just put the names of it, and you enter the variable from this menu to this menu, just clicking on the arrow. Okay? And in the between subject factor, you can add your between subject factors, so the grouping factor, and you can also add covariates here. So if you have a continuous predictor.
The other one was frightness.
Frightness is, well, this is something that is built in. You have a definition of all the variables when you open the file, but is here the frightness is how much the value is frightening people, and there is high or low frightness, and also the disgustingness, because this experiment is how much would you like to kill that bug. That the experiment, it's not mine. Okay, so you enter all your stuff, and in terms of what you can, the table is auto-generated. As soon as you enter the stuff, it generates the table that we were discussing 1 minute ago. But you can ask for more tables and for additional plots. But I think it's enough to ask for I guess the fx maybe, and the estimates if you want the parameter estimated by the model. You see, Marco, here there's a model average R square, so there's this part where you try to, this is a new feature for the new version. Okay, so that's how you define all these parts. Let's see if we can see. Zoom. Thank you. This is a very good hint for doing this. Okay, so here you see you have all the different combinations, and look at this. All models include subjects. This is something that will be deepened in the next hours, but this means that you have a random effect, which is subject in this case, and in JASP everything run with the subject as random effect. It will be more clear in the next hours. Okay, don't now. Okay. Okay. Good. So if we look at the output, basically, how to read this output. So we have all the different models, and what we are doing is comparing one model with each other. And that's what the bias factor 1,0 is doing. So it's comparing one model against each other. The bias factor is a ratio, so you have two. The comparison is always one model against another model. So in this case, we set the denominator to the best model. In JASP, you can ask to the null model or to the best model. So you can compare each model against a null model, so how data are predicted just by random effects, or against your best model. So in this case, we set the best model. So the best model is 1, of course, is one self against themselves, so it's 1. And all the other models are below 1, of course, this is the best. But you can see how much better is than the others. So we have this model clearly better than all the others, and maybe we have these two models that maybe in the next participants or next subjects can somehow play a role. So this is not the perfect way to look at this data. I think there's another stuff that we have to do before, but let's say that if I have to decide what matters in this model, I would say, well, for sure, friedness and disgustingness, because all the first 3 models include these main effects. Then maybe the main effect of gender, but we have not clear evidence to support that the gender plays a role in this case. And maybe the interaction of friedness by disgustingness. But again, if we have to take our decision now, today, with this data, we would go with just the 2 main effects as best model. And another way to, okay, so this is the bias factor, and BF of M is the bias factor of one model against an average of all the others, but it's not very used, this one. And this is instead an informative part of the table, which is, again, probability of the model given the data. So this is, we have 42% of chances that this is a best model. Of course, 43 is not that much, but this is because we have a lot of models and our probability spread all over the other possibilities.
We have different results, isn't it?
Different results is always because you sample from the posterior. So in this case, you can set the seed. So if you want to replicate exactly the same results, you can set the seed here. Under additional options, you have repeatability. You can set the seed. In this case, you will have always the same numbers. If you don't, it always pick a different seed. So you will have slightly different results every time that you run this analysis. Yes?
Is there anything to protect against sampling variation? What I mean is that, suppose this is the best model, right?
Yeah.
We have a difference of one model is studying slightly better than this. But that's one sample of data. If I do the study, again, not the seeds, but another study, chances are that this will change this result. So that's sampling variation. Is there anything in there trying to protect against sampling variation?
There's
some slide when the difference is sufficiently strong that you can say that's the difference, or if there's a point in which you can say, of course, in this sample that's better, but doesn't imply that it's better in general.
What you can do with the estimates, what you can do outside, you can do it better probably. It's having to weight to average all the models. So you can have an estimate for all the different effects, averaging all the different models, and this averaging is done according to the weights calculated on this column. And this somehow protects you because you are not saying that only the first one model matters. All the models matter according to their weight. So if 2 different models weights close one to each other, they both contribute almost equally to having this averaging. So this is, in my view, protecting from this, from what you said, because if, for example, I'm unsure if gender is part of the model or not because it's second, the model with the gender. When I do my average estimation of the parameters, I'm calculating gender for how much weight in all the different solutions. So you can have these slightly different results, but if you are averaging all the models, somehow you are accounting for the possibility, you are not excluding that gender will matter in your analysis. You're just weighting according to the evidence that you have. So I think it's going in that direction. It's not a perfect protection. Okay, so I think we can go on because it's just a quick overview of what you can do. So analysis of the effects, in this case you are just looking at the single effect. This table is more similar to a table of the classic ANOVA because you have your effect with your outcome, and in this case you have this column, probability of inclusion a priori, before the data, and how it's generated is 0.73. It's generated by summing up all the a priori probability of each model that include frightness. Because it's a main effect and in all the combination it's almost always included, a priori the probability to end up with a model that includes frightness is pretty high, because in different models there is this main effect. Anyway, after the data, the probability of including frightness is approximated to 1. You are almost certain. So if we have to take a decision, for our dependent variable, we are pretty sure that frightness matters. Because whatever the combination, it ends up with a model that includes it. Models that does not include frightness are so unlikely under our conditions that we can exclude that frightness doesn't matter. So, and you can do it for all the combination, all the main effects, and all the interaction. Of course, this changes because you see the third level interaction is present in only one model, which is the most complicated. So, in this case, the prior probability to include it is just 0.053 because it's only in one model. But again, after conditioning on the data, this probability decreases. So we can exclude. We are pretty sure that we can exclude that this third level interaction plays a role in our model. Okay, and this is the model average posterior summary, what I was saying before, and this is created averaging all the different models according to their weights. I don't think we have time to go in the details now. And I'm not very expert on how to interpret this, but I think this could be interpreted as an R-square. I didn't read a lot, so I won't go into details on this, but you have this R-square index, which in this case is 0.5, around 0.5. Okay, and you can ask also for the plots, but again, these are not the best feature in JASP because they are nice, but they are not flexible. So, for example, in this case, we have this plot there. I mean, this would be not very useful in a paper, for example. Okay, so what am I doing? Okay, we already did this, so we already discussed how to have this kind of stuff. If we take the effects request, we have the table with the different effects that I showed you before. So this one, where you have each factor, let's say, average on itself, and with its probability of being included or not in the final model. In this case, you can also ask for post-hoc tests, and there is here this menu, post-hoc tests. You can add, of course, not of course, but it does only on the main effects. So if you have just 2 levels, well, it's not that much useful, but if you have 3 levels in the effector, this might be useful. And you can add this correction, although we discussed, do you need to correct for multiple comparison? There's discussion, but you can add a sort of correction because you have higher probability to have evidence for the null hypothesis. So you can try to correct this thing just by dividing. I don't remember exactly how it does, but it's written. So the posterior odds have been corrected for multiple testing by fixing at 0.5 the prior probability that the null hypothesis holds across all the comparisons. the reference for it, but you can also have the uncorrected bias factor for the sort of t-test. And you see that if you have two levels, you're not changing everything correctly. So you can have the post-hoc test. Here it is. Okay, so summing up, pros and cons of JASP, but we switch soon. It's easy to use. It's usually fast, although when you go to complex models, it's not. You can also do hierarchical model, more complex hierarchical model, and in that case, it takes like 1 hour, maybe, or maybe 2, or maybe never finish. So usually it's fast, it's worldwide used and accepted, so it's giving a sort of standards in using and reporting, although not all the scientific community agrees with the standards, and we discussed about it yesterday. We discussed also about the fact that you cannot access the code, so you cannot change stuff, and somehow is forcing a way towards some uses, but that's it. The cons are that it's not directly accessible, the code. You have limited option for many stuff, so sometimes you don't want these things and you cannot change it. The graphical part is nice but not very useful. And sometimes the immediate automatic update of the software, it's a pity, because if you know that this analysis will take like half an hour, you want to make all the changes before it starts again to process all the data, and instead every time that you change something, it starts computing again. And you cannot block this automatic mechanism, so if you're running fast analysis, it's an advantage. If you're running slow analysis, it's good. And sometimes crash, but it's not. Everything crashes sometimes. Okay, so it's used worldwide. So my conclusion on that is that should we use JASP? Well, yes, you can. It's not mandatory. You can do all this stuff outside JASP with the same level of accuracy and speed if you learn how to use packages. But sometimes it's useful. So if you're running more basic Bayesian design, I think it's better than using other stuff, because it's intuitive, it's fast, it's easy to teach, and also for master students, PhD students, everyone can learn easily to use JASP and to run reliable, good analysis with it. But you don't have to, and if you need flexibility, you have to go outside. And flexibility is a plus of Bayesian analysis, so at a certain point, you will go outside if you start doing this stuff. Now, I had these slides, but I don't think it's useful now, but I prepared again, these are script that we will see on it. This is not extremely useful. Okay, let's go to the conclusion of Bayesian stuff. This is a sum up, and it's also done with literature, but mostly it's my viewpoint on this. So, of pros and cons and comparison between null hypothesis statistical testing and bias factor, let's say statistical testing, because it's a specific feature of the Bayesian statistics. In one case, you have rigid assumption, which is not a cons in my view. It's just that you have to remember the assumption, and you have to take in considerations if you do all the stuff within this assumption, considering it, then it gives you the proper framework to drive correct conclusions. So it's not a cons, but you have to pay attention. It's very diffuse, so that's a plus for the NHST. And at the same time, it's easy to understand and easy to misunderstood, because the fact that it's very commonly used, it gives you a common language with other scientists, but at the same time, we know how many times p-value is misunderstood, confidence intervals are misunderstood, so it's both an advantage and a disadvantage, this common language. There are good standards for reporting the analysis, and this is easier for controlling the results, for replication and of the results. But it's a directional testing in the sense that, not that it's just bigger than, but in the sense that you are just assessing how much evidence, although evidence is not the perfect word, you have against the H0. And you remember the picture of the two boxers, although this can be read in with different perspectives. The Bayesian instead is more flexible, certainly more flexible. It's powerful and sensitive, good. It's more powerful and sensitive in my vision. It can drive to conclusion either way, so both for H0 and H1. So in some cases, just practically speaking, if you have null results, it's easier to publish a paper with null results if properly analyzed with Bayesian statistics than a null result properly analyzed with NHST, because it gives you evidence to speak a little more, let's say. Sometimes it drives to not certain conclusions as NHST, but in my vision now it's perceived like a failure of Bayesian statistics, because the fact that you can prove H0 being in an uncertain situation where you cannot drive a conclusion is a sort of failure. Because you can do both and you end up with nothing in your hands. So it's perceived like more a failure in the Bayesian world than in the NHST. It can be complex. We discussed a lot about priors, and can be difficult sometimes and time demanding. There are situations where sampling from the posterior is really time demanding, so you have to really think before running an analysis with it. So this is it. There was also this tricky part, but I think we don't really need to do it. The idea was to make you answering again about the question of how likely will you do Bayesian statistics in your next experiment, and that would have been our posterior probability. So we have the prior, the data are our classes, and the posterior would have been the second judgment. So, but we don't have time. And I put a few references, basic references and resources for running all the stuff by yourself. And that's it. I think I can show you just quickly the script of one. Okay, just to make you aware of what you will have in your hands. Oh, here it is. I'm not as good as Giulio in anything, but especially in R. So I don't know if I also need all these packages, but I have some packages that I use to run in the beginning of any analysis. So you will have this file, but yeah, data puzzles. I think it's inside bias factor package, if I remember correctly. So we need to run some stuff. RCPP. I found out yesterday night that it has been updated, and if you don't have the updated version, bias factor doesn't work. So that's a nice job. Okay. So first thing that I wish to show you is that you have different functions to run a bias factor analysis. In this case, it's always a sort of t-test, because it's just one predictor with two levels that predict reaction times. It's a shape predicting a reaction time, and you see that you have general test BF, linear model BF, t-test BF, which is the one with the worst script, and ANOVA BF. All these analyses bring to the same results. So let's run 1, 2, 3, and 4, and we can see here we are in the same seed. That's the bias factor for shape. 1, 2, 3, and 4. What does it mean? It means that you have different methods to call the same function, basically. Bias factor tries to guess your the shape of your predictor, if it's a continuous or a factorial predictor. So you can use different ways of calling it, the different stuffs. And what's the advantage is that if you know exactly your the form of your variables, you can use the best call of your function, and this helps speeding up without not making mistakes in detecting the type of variable. So if you know that it's a continuous variable, use linear model more safely than, but bias factor does all the job underlying. for you if you are uncertain. So, for example, ANOVA includes the random effect by definition. If you use ANOVA BF, instead if you use general test BF, it doesn't include a random effect by definition with the subject, so you have to declare which effect is random and which is not. So there are slight adjustments, but if you're running something like this, you will end up with the same results. And oh gosh, move it. Okay, so what you can do in a more interesting way, of course, you can save this object, this bias factor object. For example, we can save in M1 a general test with the t-test, but we can see, and we can save also, in this case, you see we have a formula that defines two main effects plus an interaction. You can also make just shape, asterisk, color to make both main effect and interaction. So the formula is very similar to other situation in R where you enter a formula, but you have this function to define the random effect. You see which random ID is, in our case, the subjects. So let's run these two, and I show you what you maybe we can see M2. So if I just write M2, okay, that's the summary function basically of M2. You have, in this case, you see the denominator is declared here is RT predicted by just ID, so it's the null model that includes the random effect, the denominator, so the bias factor is always this model above this model, okay? So shape plus ID against ID, it's 2.8 the bias factor. Shape plus color is 11 times more likely than the non-null model, okay? Other stuff that you...
Sorry.
Yes?
Plus minus 132 is the credible interval?
Sorry, where is it?
Plus minus 1.
No, this is a percentage of error of this estimation.
Okay,
It's
so
because it's seminar for the posterior. No, it's a percentage of error of the bias factor estimation.
And those values are independent. For the last one, who includes the interaction effect, is 4 times. Yeah, it's.
These are always against this model, so it's always
So
4 against the denominator that is declared here. But you can do what you want to do, and I show you now exactly how to do it. It's here. So you can use the different the bias factor object I call M2, for example. I asked to use the M2 level 3, so the shape plus color, and put it in contrast with the M4. So let's say that I can do something like this, and model 3 by M2 model 4, and this gives the bias factor of shape plus color plus AD against shape plus color plus also the interaction. So in this case I have put in contrast 2 different models directly one against the other. Okay, so I can use the solution of the bias factor analysis to make new bias factors. And okay, what I wanted to show you, if I use general test BF, that's what I wanted to show you. Let's see. If I use general test BF, for example, it doesn't recognize that ID, it must be included in all the models because it's a general test. Instead, if you use ANOVA BF, it always includes the random effect in part of the model. In this case, I define that ID is random, but it also calculates the effect for the shape without random effect model. If I want to have something that is never excluded, I can use the never exclude function and just declare what must be always included in a model, and I end up with this one. You see, the only difference is that the model with only shape is not anymore available in the app. Okay, and yeah, now I don't go here, but I put the script to calculate also the parameter estimation from bias factor. It's not very intuitive and not very useful because it's not the perfect environment to run this analysis, but you can have an estimation of your parameters also. So that's it. I think it's better to stop here.
This was in bias factor or it was BMS?
No, this is all the things that I show you is with bias factor, also the parameter estimation. But if you want to run parameter estimation, it's better to go to BRMS. And I put one simple script just to have something to exercise if you have time and willing to go inside that. It's basic, it's a really basic part of BRMS, but you can try it by yourself. We need an entire week if we want to go to BRMS. I think we should stop here. Okay, thank you. Giulio, I leave you the next part.
Okay.